Hi guys, so today's lesson is actually twofold. We're going to talk about our last group ranking model that we're going to consider, which is called the Condorcet method. And then we're also going to look at a little bit of recurrence relationships on the back and talk about those a little bit. So let's get started with the Condorcet model. So our last method that we have is looking at this idea of a voting system where everyone is paired with everyone else. So what this kind of ends up looking like, is a series of runoff models, and we combine them all into one section. So each choice that we have is compared with another choice. This ranking method then we have reveals this Condorcet winner, which really means that it's the candidate whom the voters prefer to every other candidate when compared one at a time. That means that if I said, who do you vote for, A or B, and you say A, then I say, all right, what about A and C, and you still say A, and I say, what about A and D, and you still say A. So overall, this person, when they're head-to-head, which is kind of what we're looking at, they're called pairwise comparisons, but basically it means a head-to-head challenge. If we do all these different pairwise comparisons or these head-to-head challenges, and we consider all of the different options, this person who wins all of the comparisons is called the Condorcet winner. So we compare A with B, we compare A with C, we compare A with D, we compare A with E, and so on and so forth. And then we look at B versus C and B versus D, and we consider all the different types. And we're not really looking at this like 1 point, say, but we're going to look at like who wins. And we'll just use like our W here for a win, which really means 1 point. And then for a loss, we're going to use this L, and they get 0 points, and then if it's a tie, we'll just mark it with a T. And we look at all the different point values as we're looking at, and the person, if the winner here that we have wins everything or ties, it's not necessarily most number of points, but if they win or tie, then it's considered this Condorcet winner. So we're not going to really bother with actually awarding points. We're just going to use this system because it's a little bit simpler to view it that way. So let's say that we're going to use this Condorcet method with our beloved example that we've been using for the last several lessons. The best way to do this idea or organize your thoughts is to do it in a table. There's lots of different ways that you could do this. You could actually write out all the choices, but I think it's easier to view it, and the book does this too, view it in a table setting. So along one side, I'm going to put all our choices, and along the top, I'm also going to do all my choices. So how this system works, if we're going to do this box way, is that we take all the choices on the side, and then we do a head-to-head comparison with all the choices on the top. So in other words, it's comparing the row, the column. So in this first one, it would be A versus A, who wins? Well, A can't actually compete against A because they're the same, so I'm just going to put an X there. But our next one in our row here, it would be A versus B. So in this section, this means that we're looking at, kind of box it here so we can consider it. This box right here is A versus B. So we look at a head-to-head comparison in this chart of who wins in A versus B. So what that means is that we eliminate all of our choices, just like a runoff, and we look at just looking at A and B, who would be the winner there. So A is above B 8 times, B is above A 5 times, B is above A 6 times, B is above A 7 times, which means it's 8 versus whatever that is, way more than 8, which means that B wins. So in this challenge of A versus B, A loses. So we're going to give A loss. Now, to make this a little bit easier, make this a little bit faster, we could look at all the A's, and then we could look at all the B's and all the C's and all the D's. But since we've already done A versus B, that means that we'll end up seeing again, that same comparison in reverse, B versus A, and B actually wins that challenge. So I'm going to put a W there. So across the column here will end up being also, or across the row will end up also being down the column, but the opposite choice because you're looking at the opposite comparison. So if it were B versus A, B wins still. And since I'm making that comparison, that would be given a W, a win, versus A versus B, we would mark with a loss. Okay, so our next one is A versus C. So again, eliminate everything else, and we look between a head-to-head comparison between A and C. So A beats C 8 times, C beats A 5, C beats A 6, C beats A 7 times. So same situation, A loses whatever amount of times that is. And that means that A loses this head-to-head battle between A and C. And we do it again. We look at A versus D. A beats D 8 times, D beats A 5, D beats A 6, D beats A 7 times. So it's 8 versus, what is that? I just keep 18. So 18 votes would go to D, which means that A versus D, A loses that battle. So no way can A, I mean, they had one loss anyway, but no way can A be the Condorcet winner because it actually loses every head-to-head challenge that it faces. It would lose to B, C, and D. So asking an overall win of who do you prefer, A or B, most people in the majority would say B is the clear winner, and most people in the majority would say C is the winner, and most people would say D. So that would actually lose every head-to-head challenge that it faced. Again, down the column, C versus A, since A loses to C, C wins against A, and likewise, since A loses to D, D wins against A. So we keep going. B versus B is not a head-to-head challenge that we look at, so now we look at B and C. So B is above C 8 times, B is above C 12 times, and again, it has to win in a majority section. We have 26 votes here. So far, C is above, B is above C 12 times, which is not enough to get a majority. Thus far, like as soon as you hit a majority, you can stop your pairwise comparisons. But we have 12 votes so far, or sorry, 13 votes so far, which is just on the border. We just need one more. C is above B, so C wins 6 times, and up B is above C in this last one, so all of those 7 votes would go towards B in that case, so it'd end up being like 20 to 6 in a pairwise comparison, so B would win that. We keep going, B versus D, so B is above D8, B is above D5, B is above D6, and D is above B 7 times. So all 3 of these versus 7, which means that B is again a winner. Now, you can kind of glance and do these, but make sure that you actually are a little bit counting and making sure that the person that you're allowing to win or saying is a winner actually is a majority winner. Sometimes if we just like say it's above in 3 of these categories, that really doesn't matter if the last category is like 20 or something. So be careful on how you're actually looking at that and using the actual voting for it. But a lot of times we can kind of do a quick add or at least see clearly that they're going to be the winner. So if we go down the side, C versus B would lose because B won against C, and likewise D versus B would be a loss since we won against that. So we can actually see right now that B wins all of their head-to-head comparisons, which means that B is a Condorcet winner. If we did end up doing these last comparisons, we'd only end up having to do one more, C versus D. So if we look C versus D, C versus D, C versus D, looks like C is winning since D is only above C in 1 or 7 of those votes out of 26. So C wins that, which means that D loses in our next part, and then this one can't happen. So C lost a head-to-head comparison against B. D lost a head-to-head comparison between B and C, only winning its head-to-head comparison against A. So B is the only one who won or tied all of the others. If there is a situation where there's not one clear winner, then there just wouldn't be a Condorcet winner. So let's see that with this one. We'll do it one more time. We're looking at a Condorcet winner in this schedule. So again, I'm going to use my box to help us. So A versus B can't happen. If I look at our, A versus A can't happen. So if I look at A versus B, A is above B 20 times, and then B is above A 20 times, and A is above B another 20. So it ends up being 40 to 20, which means that A ends up winning that head-to-head comparison. If we look at A versus C, A is above C 20 times, C is above A 20 times, C is above A another 20 times, so it's 20 to 40, which means that A loses that battle. So if I reverse down this way, A won, which means B loses, C won, or A lost, which means C wins. B can't verse itself, B versus B, and so B versus C here, B versus C, B wins, B wins in this case, B loses. So it's 40 to 20, which means that B ends up winning this one, which means that C in our next one ends up losing, and then C can't compare with itself. So in this case, this is an example of one where we don't have wins straight across. I've got a win and a loss and a win and a loss. So there's actually no Condorcet winner. Interestingly about this idea, though, is this actually demonstrates what's called a Condorcet paradox. Now, paradox just means it's something that's against the norm, or against something, or is something that contradicts itself. So in this Condorcet paradox, what that actually is, which is something that we do need to talk about, is something that you are responsible for. This idea of a Condorcet paradox means that it is contradictory to or it has a contradictory pairwise comparison. So what that means is that A beats B, if we look at our table, if we kind of look at that. A is something that wins to B. B is something that wins to C. B beats C. So if I were making some general reason and I said, hey, if A beats B and B beats C, shouldn't it be that A beats C? But if I look at my chart here, A actually loses to C. So this doesn't actually make a whole lot of sense, which is why this is called this paradox idea. It's contradictory. It doesn't follow, and you have to be a little careful because this is definitely kind of this idea of how this actually happens. This doesn't follow what's called the transitive property. Which means it's a paradox. It doesn't follow this rules of logic. It's a contradiction in itself. So this happens in a lot of cases where we don't have a Condorcet winner. We'll end up seeing some sort of paradox actually happen. So that's our last method that we're going to look at. The last part of today's lesson is talking about recurrence relationships. You'll also need a calculator for this section, so I would get one out. Recurrence relationships are basically a statement that uses the previous number for its formula, for its equation. So it's something that is derived from the previous term. Now, we should have done this back in Algebra 2, so you should have known at least what a recurrence relationship is and that idea of seeing some of this notation. But it has two parts. One of the parts is talking about the starting value, so we symbolize that as a sub 1, meaning the first value in our terms, or in our sequence. And then we have this equation that we signify as a sub n. Now, a sub n is a function of a sub n minus 1. This means it's the previous term. And this is kind of like next. So the next term is coming from the previous term. One example of what that might look like is, say, in this recursive form, so our first term is 6, our next term that we have in our sequence is taking the previous term, a sub n minus 1, times 2. So our next term would be 12. And the next term is, again, taking that previous term, which is now 12, times 2, which is 24, and so on and so forth. This is the same recursive formula, just represented a little bit differently. So in this one, this is talking about our previous term being like the last one, n minus 1, and this is using our next term. So this is kind of like the one that we're on now. Our next one is taking the one that we are now to get to the next one, and this is saying actually the one that we are on now is derived from the previous term. So it does make sense. It's just kind of like looking at past tense or present tense, and the only difference here is looking at like what n values that were actually defined as. So we won't go into that too much, but you can see that in a little bit two different ways. Sometimes these multiple terms are depending on the sequence that you have, but at some point when we have a recursive formula, we have something defined on the previous term or next term, and we use that n value, or n minus 1 or n plus 1, you'll see that somewhere in there. So to actually see this, we're going to go through one example of how this works. Our first term in our sequence is -4. That's why it's saying is n minus 1, or a sub 1 is -4. So if our n value, kind of like our x, and our a value is kind of like our y, our first value here would be -4. And then we use that previous term to come up with our next term. So our n value, if we kind of sub that in, our next value that we're looking at is a sub 2. So if I sub that into our n, it would be a sub 2, because n equals 2, and then this would be a sub 2 minus 1, so that would be a sub 1 plus 5. A sub 1 we already know. A sub 1 is -4, which gives our next term as 1. And to get our next term, a sub 3, our n value here would be 3. So again, if I use this like equation that is defining my recurrence relationship, our n value is 3. So our next one would be a sub n, which is 3. 3 minus 1 is 2 plus 5. A sub 2 we just found. A sub 2 is our last term, which is 1 plus 5, which gives us 6. So in our next one, I'm not going to be as formal. To do this, we'd end up using a sub 3. A sub 3 we just found was 6, so 6 plus 5, which is 11. So interestingly enough, if I consider what's happening here, it generates a pattern. I used my previous term to generate what my relationship was, but if I gave you this table back in Algebra 1, you should be able to come up with what pattern this would be. I end up adding 5 every time from my previous term, which makes sense because I see that in my recurrence relationship here. When I add that same value every time, what that ends up being, if I did say plot this, which I'm going to do just a quick little graph. I'm not going to be too specific. Remember I said that this is kind of like your x value and this is kind of like your y value? If I did plot these terms, I would have our x value being 1 and our y value being -4, our x value being 2, our y value being 1, our x value being 3, our y value is 6, and our x value being 4 and our y value ends up being 11. So if I look at what pattern this is happening, this is pretty linear. And if it's linear, I know that linear equations are in the form of y equals mx plus b. My slope here is up 5 over 1, which is why I'm seeing that 5x every time. And my y-intercept, if I did kind of extrapolate here, I was at -4. My slope would be down 5 over 1, so -4 minus 5 is -9. So notice that we can actually write an equation. Which in our case is y equals 5x minus 9. And this would end up giving the same table if this were x and this were y as this recurrence relationship. And these look different. Like we can kind of see some similarities. We've got a 5 in these places, but this -9 is nowhere to be seen in this case. This translation, or what this is actually called versus this is the recurrence because it's based on a previous term. But this equation where I can just evaluate at any x value I have, like I can plug in x equals 4 and it'll pop out 11 at me. This is called the explicit. Or solution. Solution to the recurrence relationship or the explicit form. Both of those mean the same thing. It means that I have a function here that I can use explicitly to come up with my next value. Now there's some benefits to that. If I wanted to figure out what my a sub n would be at n equals 100, the recursive model would not be a good model for me to use because in order to get the 100th term, I need the 99th term. And in order to get the 99th term, I need the 98th term. In order to get the 98th term, I need the 97th term, and so on. And I'd have to keep going backwards and backwards and backwards until I get to a value that I know so that I can build on that and go forwards. The explicit form is really easy to find the 100th term. I just plug in 100. I have 5 times 100 minus 9, and out pops the value of what I would know would be the 100th term. So the explicit formula is really easy in that regard. However, there are some things in nature that just occur recurrence relationship or recur in a recurrence form. The Fibonacci sequence is something that is a very natural sequence, and it occurs as it's the addition of the previous two numbers. So 1, 1, the next term would be 2 because it's 1 plus 1. The next term would be 1 plus 2, which is 3. The next term is 2 plus 3, which is 5, and so on, and it keeps going. And that's a really easy equation to write as a pattern, a recurrence relationship, as looking at the sum of the previous two terms. But the explicit formula is actually pretty hard to find for that one. So they have benefits in both ways. They are used interchangeably in a lot of different functions, or finding, like, say, the recurrence relationship and finding the explicit form that matches it. We do those things in both ways, and so it's beneficial to know how to do those both things. For your purposes, actually finding the explicit form we'll end up doing a lot more later on in the year and in the semester. For now, coming up with the table that matches your recurrence relationship is the most important part. Knowing how to deal with that is something that you should be expected to do. So let's just do one more quick example. This one's a little bit different. I wanted to throw something at you that was a little not as, say, easy as the last one. So we have our recurrence relationship that's defined. Again, that's this part. This one looks a little bit different because I'm using a sub n plus 1 versus n minus 1 in our problem. But again, that means the same thing. We're just looking at the next term, or defined as by the previous. So in this one, a sub n is the previous term and a sub n plus 1 is the next term in our sequence. So they give us a sub 1 is 3, and they give us a sub 2 is 7. So again, if you get confused with how this works, I like to pick like an n value to help with us. Now, what I actually want here is, or what I'm looking for is a sub 3. So if I was looking for a sub 3 here, n would actually have to be 2. So that I would get 2 plus 1, which is 3. So our next term that we're looking for, a sub 3, my n value would actually have to be 2. So if n is 2, I'd have 2 plus 2 times a sub 2. All right, a sub 2 I know is 7. I can see that from my table. So I have 2 plus 14, which is 16. So that would be the next term in my sequence. Now that I've figured out this harder part, like knowing what this value should be, this n value should be to get to our next term, we can just go in order. So our next n value is going to be 3. That would achieve us or get us 3 plus 1, which is 4, a sub 4. That's good. That's the next term that I need. So if our n value is 3, then it'd be 3 plus 2 times a sub n equals 3, so a sub 3. So 3 plus 2 times a sub 3 is 16. So 3 plus 32, which is 35. That's our next value. Again, if we would go again, our next value in our sequence would be 4, n equals 4. This would get me, looking at my recurrence relationship, 4 plus 1 is 5. That's good. That's what I need, a sub 5. I need that value. That would be 4, because n is 4, plus 2 times a sub 4. Again, n is 4. So a sub 5 would be 4 plus 2 times our a sub 4 is 35, which gives us 4 plus 70, 74. So that one's a little bit more difficult in 2 parts. We have this n that's kind of weird to deal with in this one, but then also because we're dealing with that n plus 1, it makes it a little bit harder to actually deal with like where we're starting. Now, if you didn't know that, if you're like, well, I'm going to try n equals 3 because that's like the next one that I had. If I did do that and plug things in, I would end up with a sub 4, and then I'd be like, ooh, I don't have that one yet. So I have to go back an n value, which is why we had to start here at n equals 2, actually, to come up with my next value, a sub 3, in my sequence. Again, the most important part is dealing with like these two, and you'll get some more practice dealing with how to actually come up with these sequences in the book assignment on page 20, but then also you'll get some more practice when we do our practice worksheet too. You'll have a little bit more of generating that kind of idea, but make sure that you do know how to figure out how to come up with these values in, say, or come up with these tables in, say, a quiz setting.